Greetings. Let's talk about differential equations. To start with, let's look into how this ties into other classes you've taken in the past, other subjects you've already seen. In a typical calculus curriculum, for instance, you usually start with the idea of derivatives. Given a function, and I'm going to assume this is a function of t, because often we talk about how something's changing as time passes. So I'll just be using t as the default independent variable. Given some function of time, you want to find its derivative. dy dt, also known as y prime. You want to know how fast is the function changing as time passes. First quarter calculus or first semester calculus, typically all about, given a function, find how fast it's changing. Second quarter or second semester calculus is usually the reverse of that. Given the derivative, you want to find the function itself. And typically you'd be doing that using an integral. Y is the integral of its derivative. Given a derivative of the function, you can usually integrate to find the function itself. Differential equations kind of combines those two approaches and complicates things a bit further. In differential equations, the idea is we don't know the function or its derivative, but we know something about how they're related. Given an equation describing how y and its derivatives are related, we want to find y, and possibly its derivatives as well. But of course, once you find y, then finding its derivatives goes back to a Calculus 1 problem. The important thing is, given the relationship between y and its derivatives, you want to figure out what those actually mean. So let's try out some examples, or investigate some examples. For instance, in a Calc 1 problem, maybe you have y equals 3t squared. And you want to find the derivative. Taking a derivative, usually a pretty straightforward process. Each type of function has usually a certain formula that you just jump straight to. 3t squared, for instance, t squared becomes 2 times t to the first, so we get 6t. Or in reverse, let's say we have y prime equals 6t. So we find y by integrating that. Add 1 to the exponent, divide by the new exponent, 6 becomes 3. And since we're looking for all possible solutions, we should also include plus some unknown constant. In this original, the unknown constant happens to be 0, but the idea is if you know the derivative, that doesn't narrow it down to one specific function. There's infinitely many functions it could have been. And that's often going to be the case in differential equations as well. If you know something about the function and its derivatives and how they're related, typically there's a whole family of infinitely many functions it could be. For example, one particular differential equation, probably the simplest possible differential equation that doesn't just resolve to a Calc 2 problem, would be, let's say you happen to know that y prime equals y itself. You've got some function whose derivative equals the original function. And take a moment to think back to what you remember from calculus. What's a function whose derivative is itself? If you remember from calc, that should be e to the t. However, that's not the only one. You take the derivative of e to the t, you get e to the t. But also suppose you had like e to the 3t. The derivative of that, you keep the 3 as a constant multiplier. Derivative of e to the t is still e to the t, so y prime is still equal to y itself. In fact, it's not just e to the t or 3e to the t, it can be any constant times e to the t. So the general solution to y prime equals y is y equals some constant times e to the t. Any such function will work because when you take the derivative, the c stays the same since it's a constant multiplier, and e to the t stays the same because it's e to the t. So this is the general solution. It's all possible solutions written in one formula. Now you can narrow that down to one particular or one specific solution if you have one more piece of information, usually called the initial conditions. Let's say we're also given that when t is 0, y is 5. You can plug that in. You can replace t with 0, replace y with 5. E to the 0 is 1, so that means c is 5. So y equals, if we make that substitution, 5e to the t would be the specific solution. Ce to the t is the general solution to this differential equation. 5e to the t is the specific solution to this initial value problem. An initial value problem being a differential equation and initial conditions, typically representing some single point that the graph goes through. So there's infinitely many solutions to this differential equation, but only one of them passes through the point 0, 5. So that's the basic idea of what a solution means. The general solution is a list of all possible functions that make this differential equation true. The specific solution is the one of those that makes the initial conditions true also. One other topic I'd like to mention at this point is the idea of order. Unlike derivatives and integrals, where there's typically a pretty straightforward step-by-step process to getting to the answer, there's no one method that works for every differential equation. So generally what we do is sort of a divide and conquer approach. Categorize the differential equation. Once you know what category it's in, there's typically a type of method or a collection of methods that works for differential equations of that type. And one of the most important categories is the idea of order. Order is basically just the highest order, the highest derivative in the equation. The highest derivative in that differential equation. And you may see some more complicated, more involved definitions of exactly what order means for certain other categories of differential equation. But for the kind we're going to be working with, order just means the highest derivative in it. So for instance, y prime equals y is a first order equation because it has a first derivative in it. If we had something like 3y double prime plus 2y prime minus 5y equals 6, this would be second order. Or if we had the fourth derivative of y equals y squared times the second derivative of y plus t squared, this would be fourth order because it has a fourth derivative. So in general, an nth order differential equation will have an nth derivative related to possibly all or any of the prior derivatives as well. So that's the main idea of order. And as you might expect, first order is typically the simplest ones to solve, so that's what we'll be starting with. We'll also get into second order equations. Third and higher often follow pretty much the same patterns as second order, at least given certain constraints. So first and second order are usually the main ones to consider. So let's try another first order equation or two and see what we can figure out. Y prime equals y is pretty straightforward. You just get something times e to the t. Let's make that one step more complicated. Let's say we have dy dt equals, let's say, -1/2 times y. So now instead of having dy dt, instead of having the derivative be the same as the function, the derivative is a constant multiplier times the function itself, exactly -1/2 times the value of the function. And there are a few ways to solve this. One way is, if you investigate the differential equation, you might be able to figure out, oh, I know a function that has that behavior. So try taking a moment, investigate this differential equation, ask yourself, do you know of any functions where the derivative is exactly -1/2 times the function itself? So take a moment to think if you know anything of that format. If not, there are, of course, methods to figure it out in other ways. One way is by making a reasonable guess and see if you can get the guess to work. This is often called the ansatz method. You make a reasonable guess, usually with some variables, and then check if the guess works. In this case, this is very similar to the y prime equals y that we were looking at earlier, with this one modification. So we might be able to make the guess that something similar is going to work. Let's guess that y equals not exactly e to the t, but e to the something t. Because if the derivative is the same type of function, just with a constant multiplier, presumably e to the something t will work. So we'll make the guess y equals e to the rt, where r is some as yet unknown constant. To figure out if that works, we need to plug that back into the original differential equation, which of course means we'll also need the derivative. Derivative of e to the rt would be r e to the rt. So we can replace y and dy dt in the original equation with these formulas. dy dt becomes r e to the rt, negative 1/2 times y, which is e to the rt according to our guess. At this point, we have an e to the rt on both sides, so we can divide both sides by e to the rt, cancel that out, and we're left with r equals negative 1/2. This tells us two things. First of all, the fact that this equation even works means this guess is valid, that e to the rt is what the solution is going to look like. And second, it gives us an equation describing what r has to be, or at least what constraints r has to follow to make this work. So substituting that r value into our guess, we get y equals e to the negative 1/2 t. And you can always check your answer by plugging it back into the original differential equation. Derivative is going to be negative 1/2 e to the negative 1/2 t. And if you plug that in, negative 1/2 e to the negative 1/2 t is negative 1/2 times e to the negative 1/2 t. So this works. This is a solution. It's not the only solution though, because just like last time, multipliers will not change that, constant multipliers. So y equals c times e to the negative 1/2 t turns out to be the general solution, since any constant multiplier won't change the fact that this equation is true. So that's the ansatz method. You make a guess, and then take its derivatives, substitute all those into the original differential equation, see if it works. Another method that's often useful, specifically for certain first-order equations, is the idea of separation of variables. The idea is it would be very nice if we could just integrate both sides to cancel out the derivative. But the problem is if you have dy dt equals negative 1/2 y, if you just try integrating both sides, you've got to integrate with respect to t. On the left side, that's fine. Integral and derivative cancel out, we just get y. But on the right side, we can't integrate y with respect to t if we don't already know what y is, since y itself is a function of t that we don't know yet. So that's not going to work yet. What we're going to have to do first is move the variables around algebraically. So we can modify this. Let me write this with a little more space. If we modify this by first getting this split up, because we don't want to have y's and t's mixed together. If we multiply both sides by dt, and then we have y's and t's mixed together, so we'll also want to divide both sides by y to get rid of that. And some mathematicians might complain that dt is not just a thing you're dividing dy by. dy and dt are not individual numbers. dy dt is a notation. But what we're really doing here is a shortcut for a longer step-by-step method involving the chain rule. This still gets the same result. So in practice, it doesn't really matter. It gets you the same result. 1 over y dy equals negative 1/2 dt. And at this point, we have separated the variables. We have just y's on one side, just t's on the other side. We can just apply an integral to both sides and carry that out. Integral 1 over y dy, you may remember from calculus, is natural logarithm of y. And make sure you remember that. This integral is going to show up all the time in differential equations, because separating variables often leads to a 1 over something. Equals, and then on the right side, negative 1/2 is a constant, so the derivative, or integral, is just negative 1/2 t. Also, since we're looking for all possible solutions, we want to include plus a constant. At this stage, we've gotten rid of all the derivatives. This is no longer a differential equation, it's just an algebraic equation, and we can get rid of the logarithm by exponentiating. E to the power of the left side equals e to the power of the right side. On the left side, Exponential and logarithmic functions cancel out, so we just get y equals. On the right side, we can split this up. E to the power of something plus something, we can use the product rule for exponents. E to the negative 1/2 t times e to the second thing, e to the c. Also, since c is just an arbitrary constant we don't know yet, e to the c is also just an arbitrary constant we don't know yet. So let's just call that another arbitrary constant. We'll call that, let's say, capital C times e to the negative 1/2 t. So there is our general solution. Y equals some constant times e to the negative 1/2 t. Same thing we got by using the guess method, the ansatz method. And as usual, if you have an initial condition, you can plug that in and solve for C. So that's the separation of variables approach. And this only works because this original differential equation is separable. This doesn't work on all equations, it only works on certain categories. The basic idea is if dy dt equals something that can be written as a function of just t times a function of just y, then you can split that up by multiplying by dt, dividing by g of y, and then integrating both sides. So it only works if you can write it in this format. But for equations that can be written in this format, it works remarkably well. One other method, more of a visual or graphical method I'd like to investigate, is called a direction field. A direction field doesn't give you the exact answer like these analytical approaches do, but it's a very useful way of visualizing what's going on and getting an idea of what the solution should look like, even if it can't be solved directly. So a direction field, or sometimes called a slope field, is essentially just a way of visualizing or drawing the differential equation itself. The main idea is any differential equation tells you at a certain point, at a certain value of t and y, what is the derivative going to be. And in this case, it doesn't depend on t, but more generally, a differential equation is going to be derivative of y with respect to t equals something about t and y. So if you have a t value and a y value, if you have a point on the ty graph, the differential equation tells you the slope at that point. We can graph that by drawing ty axis and drawing what the slope would be at each point. For example, in this case, if we just start plugging in t and y values, t doesn't matter, but we can plug in y values. Let's say y is 0. Plug in 0 for y, you get 0 for the slope. So if y is 0, your slope is going to be 0. And note that t doesn't matter here. If t is 1 and y is 0, we still get a slope of 0. So I'm just going to draw horizontal line segments representing the slope at each of those points would be 0. And of course, we don't even know if the graph goes through those points. But if it does go through those points, it has to do so with slope 0. Or let's say we plug in some other values for y. Let's say we have 1, 2, 3, negative 1, negative 2, negative 3. See what this looks like. If y is positive 1, positive 1 times negative 1/2 would be negative 1/2. So if the graph goes through this point, it has to do so with slope negative 1/2. And again, the t value doesn't matter. If we go to the right or left, we still get the same slope, negative 1/2. So I'm just going to draw all those out. This region, by the way, this region where the slope is all one value is often called an isocline. Iso meaning same, cline meaning slope, as in inclination or an inclined plane. So an isocline just means a region where the slope is all the same. So this is the region where the slope is negative 1/2. Likewise, if we wanted to say, let's say y is positive 2. Plug in positive 2, you get negative 1 for the slope. So on this entire region, that would be an isocline, all the locations where y is 2, all those points would have slope negative 1. And this is just a rough sketch, not necessarily to scale, but these should all be slope negative 1. Or if we go higher, if we make y equals 3, then dy dt is going to be negative 3/2. So even steeper downward slope. And likewise, we could plug in negative values. Let's say we plug in negative 1 for y. You would get positive 1/2, so you'd have an upward slope. for every value, every point where y is -1, the slope would be +1/2. Or if we plug in -2 for y, you get +1. So everywhere where y is -2, the slope would be +1. Or if you plug in -3 for y, you get +1.5, +3/2. So you'd have a steeper upward slope. So this would be a reasonable sketch of the direction field or slope field for this equation. The differential equation tells you the slope at every ty coordinate. The direction field shows you the slope at every ty coordinate. And it doesn't really have as much information because, for instance, there's going to be, of course, gaps between where you draw it out. But you could always draw it in more detail if you need to. But the important thing about the direction field is it allows you to draw out sample solutions. For example, if we know that the solution curve has to have these slopes as it goes through these points, we could sketch in an example of a curve that has slope like that. Or another example, just a curve that goes as parallel as possible to the slopes shown on the direction field. Or maybe this one. And one important thing to keep in mind here is that these sample solutions, often called integral curves, they cannot cross. Because if you had two integral curves that cross, that means there's some location where there's two different slopes. That's impossible. The direction field has to represent this first order equation that says at a certain point there's a certain value of slope. If you get to second order and higher, that changes. But for first order, the sample solutions shouldn't cross because you can't have two different slopes at the same point. So if you draw in a few more of these are sample solutions. In fact, there's even one. If you start at y = 0, you're going to stay at y = 0. That's called an equilibrium solution. And we would call this stable equilibrium because everything else nearby is converging towards it. Whereas unstable equilibrium would be everything nearby is diverging away from it. And we can look more into equilibrium values later. But these are some sample solutions, and note that there's infinitely many of them. There's infinitely many curves that follow this direction field. But to narrow it down to one solution, what do you need? You need initial values. So let's say we happen to know the initial value. Let's say we know that when t is 0, y is 3. We could mark that on the graph. There's our initial value. And we could draw the one and only solution curve, the one and only sample solution that passes through that point. And that's going to look like this. So the idea of the direction field is tremendously useful for sketching out what the solution should look like, and even the one specific solution that goes through the initial value that you care about. And moreover, just by sketching the direction field, we can get a very good idea of the overall behavior of the solutions. Even if this isn't something we can solve, drawing out the direction field gives us an idea that all the solutions approach 0 as time goes to infinity. So this might represent some sort of situation where the value, if it's a positive value, it decreases towards an asymptote of 0 as time passes. Or if it's a negative, it decreases upwards towards 0 as time passes. And even if we hadn't already solved this, the direction field, the shape of the solutions here give us a very good idea that exponential decay seems to be what we're looking at. So direction field is very useful for analyzing differential equations, analyzing the behavior of the solutions. Even if it's not a differential equation, you can solve analytically. So I think that's about all we need for the intro at the moment. We can look into the more detailed versions of these approaches, the separation of variables, the idea of guessing a solution and seeing if it works, and the idea of using a direction field to analyze the behavior. We'll look into each of those in more detail in future videos, but I think this should be a good start. So, I will see you next time.